This is a Heathkit IM-12 Harmonic Distortion meter. I recently picked this one up and I was told that it was in good condition. I will tell you that with the exception of what I will otherwise note, this is in mint flawless condition. I could not believe it. I've never seen one that looks like it was new out of the box. I'm actually hoping that there'll be a reasonable amount of work for me to do inside this unit. And of course there will be, obviously. But I know that I have a reasonable expectation that I'm not going to find any horror stories in here. This harmonic distortion meter measures the total harmonic distortion just like other meters based on the fact that the theoretical perfect sine wave, which doesn't exist, will have other harmonics that can be seen. If you look at it on a spectrum analyzer, you'll see them. And basically, if you could remove that fundamental sine wave, you could then measure just those other harmonics to basically figure out what the percentage of that is based on the 100% you originally started with to come up with the percentage of distortion. Now, I realize this is an oversimplification of what total harmonic distortion is, but I can make an entirely separate video on this matter. This is not the only harmonic distortion analyzer that I own. I have another one, and that is, of course, the HP331 Alpha, an entirely different class of device, of course. This would have been much more expensive. It's much more sensitive. I've also made videos about the use of this device and the restoration of this device. I'll include a link right over here about that. What I would like to do is go and take the Heathkit device, restore it, use precision components in the restoration, and then just like I did with the impedance bridges of the Heathkit versus the Genrad 1650, is put the Heathkit up against the HP and see how close they are to each other in their accuracy. Again, spoiler, I will imagine the HP is going to win, but it would be interesting to see how close they come. To point out all of the flaws I found on this unit, this will be very quick. These connectors here got crushed. These are very easy to fix. I have to take a strong rod that is the size of those banana connectors, or even a banana connector itself, banana jack. You stick it in there and you straighten it out until you could take a double jack and fit it in properly, and that'll let you know that it's flush. Also, a slight dent up here, but that's okay. I'm not going to try and fix that. It gives it nice character, and there's no problem with the paint anywhere in this box. Everything else, like I said, is flawless. There's nothing else to talk about with regard to any defects in this unit, aside from little tiny scratches and whatnot here or there. I'll point out really quickly, there have been several evolutions of this right here. This is not a knob. This is a dial, actually, a frequency dial, which did not need to be accurate, but it was basically just supposed to tell you where the tuning knob was, and you can see it's moving. And I guess as a cost-cutting measure, they just simply used a knob for it. I've seen other ones. I've seen in some of Jeff's videos where they actually used an gnarled knob that was smooth to give you an indication that you weren't supposed to turn it. On this particular one, you could see it's just an off-the-shelf knob. You would not know that just by looking at it, that this is something you should not turn. You would think that this was actually something that you would turn. I think that it's very strange that they use something like this, and it's the only time I've ever seen it on a Heathkit. And by virtue of the fact, you can see that when I turn this, it cuts off at just after 100, which means that I was definitely not, or this has definitely been turned by somebody before and knocked out of balance, as it doesn't go all the way to 200, it stops here. Aside from that one particular issue that I found, all of the other knobs seem to be operating well. I've gone through these. The level one seems a bit gummed up. as compared to the balance. The balance feels like a wire wound resistor. You could always feel that when you turn it. And level just seems like it needs a little work. And the on-off switch is just a positive clicking on-off switch. Meter is pristine. There's not a scratch in that plastic. I'll also point out it does have the handle on it. See a little bit of dirt here, but this is just dirt. It's not a stain. I already checked. Finally, I see the original screws are in the back of the unit. That's always a good sign. In what is always the greatest part of every Heathkit restoration, or the saddest part, depending on what you find, is the opening of the unit. Let's see what we got. We already know it's from a smoke-free environment. That much was figured out. Inspection of a case shows a little bit of dust, no exposure to any elements, no exposure to smoke, no exposure to anything. This is perfect. There's just a ton of room to work here. We see several tubes. 1, 2, 3, 4, 5, 6 tubes. One shielded. I see a multi-can or a multi-cap right here, electrolytic capacitor. I'd have to flip the unit around to see how much. I see 300 microfarad. It may only be a 300 microfarad. I stand corrected. I see another one up here. Looks like 2 microfarad. These are ones that are definitely going to have to be checked. No problem at all. There's a container here that's separately shielded, probably due to some sensitive circuitry in there. So let's take this off and have a look. And that is Heathkit branded vacuum tube right there. We're going to go through all the tubes and test them individually. Let's take a look under the unit now. Not a whole lot of components up top. Yeah, so we could see that big capacitor up top, that 300 microfarad, is in fact just a single capacitor when looking from it below. So I stand corrected. Looks like the filter cap is a 2020 right here. It's a paper cap. That's going to have to go. We could see some robust resistors right here. I don't want to flip them just yet to see what they are. And I see another capacitor here I definitely want to check out. I want to ensure that the values in this particular unit exceed what they originally were supposed to exceed, so that it will operate as good as possible. Heathkit had limitations in meeting their price point back in the day with what they were able to put in these units, obviously. And a lot of times in magazines, there were recommended corrections to Heathkit units to make them superior to what they originally were. I'm trying to meet that, of course, not to modify the original circuitry, but just to use higher quality components to do so. We can also see, if we look in here, there are a couple of wire-wound potentiometers not available on the outside of the unit. It looks like for the purposes of internal calibration. I'm sure that will reveal itself in the manual as part of the calibration procedure. Another one of those wire-wound calibration potentiometers also sits on the rear of the unit. However, this one is exposed and can be adjusted from outside the unit, but it's designed that it doesn't have a knob on it. It's part of the calibration setup, but could be done with the box closed for whatever reason. Opening the top portion of the shielded area reveals only the open air capacitor for tuning. We can see that if I turn the tuning knob, it's just the open air capacitor. So there's nothing much more to see under there. We're going to go to the underside, which is also shielded, and see what's available under that portion of it. It's worth noting that within this shielding is a hole, and if we look down in the unit, there is a provision down there. It may be for a small capacitor way down in there. We'll have a look when we get to the other side. That's adjustable to get a tweaker screwdriver through there for some sort of calibration adjustment. The other side does, in fact, have a small adjustable capacitor. That's what that is. We can see another cap in here. And then finally, we see on this switch, which is the set level and different position switches here, are a series of resistors, and these resistors look to me like they are 1% resistors, and I'm sure that they're relatively close. You'd be surprised after all these years, especially something in this condition, but I'm sure we can get them even closer if we're willing to spend $1 or $2 and ensure that this is maintained. It must be a very important circuit here with double shielding on both sides. If I look down here, I see another resistor of no great tolerance significance, and then something that looks like a capacitor down there, and I can't get it in the video because it's covered, but that capacitor is within a 10% range. It's a 4.7 microfarad capacitor within 10%, and I bet that could be improved upon as well, right? So there are things within this unit where it really doesn't, you don't have to get it to 1%, but there are things in this unit that I would like to have exactly and perfectly as much as possible. On that note, when we get to the sensitivity switch right here, we also see a collection of both resistors and capacitors of extremely high tolerance running across this switch. So it's very important that close attention is paid to this as well. I see, for instance, a particular capacitor reads 7.5 with a plus or minus of 5%. So that's worth noting. I see resistors here that are all 1%, and quite honestly, I can't read this one, but I'm sure that the tolerance of this one is also very high. Before anything, though, I got to fix the only broken thing on this unit. These got to be done first. I use the cheapest Chinese banana clip adapter that I have. Not only does it straighten it out, but it pulls out the steel too. And then I'll go in and inspect. I have a little bit more here. A little bit more there. There we go. First thing I'm going to do before anything is remove this dry electrolytic capacitor, and I'm going to replace it with capacitors of the same value. I'm not going to blow up a power transformer, you know, in the event that there's a problem for nothing. Should never use these dry electrolytic capacitors. What I will do then is see if there is any benefit to adding on capacitance to clean up the power supply, the DC power supply. So we'll go into that afterwards. And that right there, it covers the first prerequisite for being able to turn on this unit. I've got a 22 microfarad and a 20 microfarad. You can't tell looking at it, but these are actually floating a good way under here. It looks like they're sitting on top of it. We're going to take a look really quickly at the old one and see what the condition was if I was just to go and fire up this unit. Now I've shut the light for this event. We're going to test the first half of this capacitor now. We're on leakage. We'll give it a second. Like, to be fair, of course, you know, you have to let this capacitor have a minute to build up. If it took longer than a couple of minutes, I'd call it a failure, but, you know, obviously I'm waiting. We can see that the eye opened up right here. I'll put my hand here, make the eye easier to see. So we're 200. And finally, after another couple of minutes, 250. We can see it's definitely slowing down here. 300. So we can see it passed the test at 300. We'll go to 350 now, which is its final limitation. I have to look at the schematic and see what actually goes through this thing. You know, if it passes, great. It means the thing wouldn't have exploded if I turn it on. You can see obviously it needed to be built up. You know, it would have benefited from a variac, definitely. But I wouldn't run them anyway because I never know when these old paper ones are going to fail as an insurance policy. So there's 350 right there. I'm going to go to the other side. I'll let you know how it turns out. I'm not going to go through this whole process for the other side. We can see the other side finally opened at 350. This one took twice as long as the first side. That said, the capacitor did work. It definitely would have needed to come up on a variac, in my opinion, without damaging anything, either from minor damage to major damage or stressing the components. Either way, the capacitor is going to go in the garbage now, but I just wanted to have a good look at it. So I'm going to discharge it, and we're going to move on. So we look at this power supply here, and we see that this is the, this is the transformer and the rectifier, and these are the two capacitors that just replaced, the two 20 microfarads, and we see this CRC right here, this filter setup, followed by a second Wirewound resistor, and then it goes into an OA2, a voltage regulator, which are pretty cool to watch when they light up. They got sort of a purple haze to them. Comes out of that, we have another voltage dropping resistor, this one another 2-watt variety, and then we got this 300 microfarad capacitor, another filter, and this designator, this positive tap right here, is designated as A, and I can already tell you throughout the schematic diagram, A is the tap for all the DC voltage and the plate voltages and everything else that feeds off of this whole unit. Is an extremely filtered, extremely stable, 150, not 150 volts, but whatever the pin 1 is minus this voltage drop here. I got a listing somewhere. But whatever it is, it's an extremely stable, extremely clean DC voltage. Right, and I got this 300 microfarad capacitor that's sitting in there, and I don't have a 300 laying around to replace it. Right, but what I do have is a 200 rated slightly higher. All mine are 160, so the rating is fine. So I got a 200 and I got two 80s, right? And that would add on another 60 microfarads onto this. I don't know, it definitely wouldn't hurt filtration, right? I don't know how Heathkit calculated 300 with regard to diminishing returns and cost. You know, would this circuit have benefited from 350 or 400 vice 300? But it was determined that it would have cost too much money, so they split the difference. I think we can find out by setting up a temporary 300 circuit with the 200, adding the 80, and then make it 280, and then seeing how much cleaner we could get this with 300 by using the hand tech, even the Tektronix, and seeing what kind of AC product we have in there. Because the 20s have already been changed out, I can simply clip this one out of circuit, make it benign, and then set up something here to get a good look here at this A voltage. If I remove this from circuit, I guess we could just have a floating voltage here to look at. The problem is, if we don't have any load on this, we're really not going to be able to see if we're having a lot of benefit, because a circuit without load seems to look better with regard to any of those AC components on there from filtering, as opposed to a circuit that's heavily under load. And that comes back to, if there's a need to turn on the device, I have to stop here, because that means all the tubes need to be checked to make sure there's nothing gassy or shorted or what have you. So we're going to break here and fire up the tube tester. 6x4 is good. I shut off the light to test the OA2. This one is showing weak, but I don't know if it's the tester setup or what, but I'll just hit the button. You can see the purple glow. It's really cool, especially if you get a good look at it. But it is showing weak here. We'll see if it's putting out the proper voltage when we have it in the test set. It's not broken though, so we'll move on. 12AT7 is looking good. We'll move on. 12BY7 also looks good. The 12AX7 is nothing to write home about. It's not broken, but it's not wonderful. I got like 7 of these, so if this proves to be a problem, I will swap it out. I'll probably swap it out anyway just to see if it provides any difference, but I'm just making a notation of its performance. Good thing the 5879 was good. I don't have any of those laying around. That concludes the tube testing. So voltage regulator possibly weak. 12AX7 looks a little weak, but I don't care. Other than that, nothing's going to explode when we fire it up. Took this opportunity, of course, to clean the dust off all the tubes And when the tubes are out, I clean the dust off the chassis, transformer, and what have you. I'm going to take the tubes out one more time individually to get some Deoxit on the contacts. Go something like this. And just get them out. Get this like that. Get the contact sprayed. Put the tube back in. There's enough to go around to get it in and out a couple times. You can feel the tension change once the Deoxit's distributed on the pins themselves. See the pins get wet, and at that point is fine. I just leave it in there, and it's done. And while all the tube sockets are drying, I'm going to hit especially this one pot right here. This one is really really tight. See if we could loosen that up. Oh yeah, that makes a difference right there. Oh, like a million miles. So we'll let that soak. Grab that drip. We'll let that one soak and we'll hit it again. And I'll hit all these contacts. I mean, the board's already wet, the table's wet. Why not get this done, move on. Now, this is interesting because if you look here, this is a potentiometer, wire wound resistor on the back of the unit. I haven't added any Deoxit to this. I've left this one alone, if only so we can have a look at this, because this one is not encapsulated by any metal. We could have a good look at it. From where I'm sitting, and the camera can't see this, but from where I'm sitting, where this copper piece is making contact, the entire area is green. There is an oxide that formed. There is no connection. So what I'm going to do is I'm going to move this pot so we could have a look. There we go, and I've moved it. And I'm going to see if I could get that camera to zoom in. It's really tough to do, but we could see a green spot right there. There we go. That's as close as I can go. And you can see where the setting was for this potentiometer and the oxide that's formed on it. And what I'm going to do, obviously, I'm going to have to clean this. So I'm going to spray this. I see there's like a cardboard material. I don't know what it is, a cardboard or probably not asbestos. But what I'm going to do is I'm going to put a little bit of Deoxit on here. I'm going to dab a little bit on, and I'm going to work that back and forth, and we're going to see what happens. So right now I'm applying Deoxit, and I'm using the screwdriver to turn it back and forth. Just to see how effective it is. And obviously you can see like a little green stain behind, but it has removed the oxide and no doubt restored the connection to this resistor. I'm sure that if I went and did a sweep test with a VTVM, that this would look just fine, or it's well on its way. Definitely the wiper that's moving back and forth here is all sorts of shiny right now where the contact point is. So afterwards, we're left with a little silhouette of green, but it was all cleaned up. The Deoxit worked. Obviously, I'll check this for sweep, but yeah, we'll be able to move on. I'm going to bring this roughly back into that known position. And we can see that the same holds true for the other potentiometers as well. We have that green spot. I'm going to be handling it in the same fashion. If there's any other potentiometers that I've missed, I'm going to go through them and treat them in the exact same fashion too. And we can see it clean up very nicely. I'll put it right back into position to move on. I'll tell you quite truthfully, I'd be surprised if this potentiometer made it, this top one. I'm hearing a lot of chatter in here, a lot of mechanical noise. If it made it, great. You know, maybe it's just going through a phase or something, but yeah, I don't know. Just to be sure, I've hooked up the IM-11 to that potentiometer that was sounding funny. And what I'm going to do is some sweeps up and down. We're going to look at the deflection. We're going to make sure it's okay. And here's where I've connected it from the middle to the end point. I'll do middle to end. We'll see what we got. The IM-11 is a fantastic VTVM to be able to test the sweep. You could really see if everything's working very specifically, if there's any abnormalities whatsoever anywhere in the pot. And so I begin. And the pot looks good. Stopping at around 45. I don't have this set up perfect zero adjustment, but I'm just checking the sweep. So that looked good. Let me move to the bottom. Bottom sweep will work with the dial turning in reverse. Move it nice and slow. Yeah, appears the dial's okay. So there we go. I just wanted to be absolutely sure. I think this thing is safe to turn on at this point. Yeah, I forgot there is one more thing left to do, and that's address this 300 microfarad capacitor. This needs to come out of circuit, so we're going to remove everything from this positive. Generally, these DC power supplies should have their grounds in a star configuration wherever possible. For the purpose of the power supply, it's always a good idea. You could see that so much so that what they did was they actually ran a connection from the ground of the capacitor, an extra cable up here, and a connection from here, an extra cable up here, to bring the ground from the old original cap together to provide that star right here. What I'm going to do in actuality is, and I'll just grab a cap right quick so we can see that here, is I'm just going to bring the caps right off of that star ground, right? And then to a standoff that I have yet to install, and then bring all the positive connections to the other side of that standoff. When I order standoffs, I order the 5 standoffs. That way I could cut them down to the size I need. And the middle one is always a ground one. And we're obviously not going to use the ground, but this is going to be the lugged one. And then I could remove this top portion, and then we'll have the insulated one here, and this will be the positive connection. So it can come down here, right, and then provide positive connection for all of these. And I've snipped off this lead off of this capacitor, making it inert. It's now a showpiece. You can see I'm lifting up everything right now. This is now flush, this piece of the capacitor. So it's now, the can is on top just for looks. It does nothing anymore. This ground wire here exists to provide a ground to this capacitor. I don't know if that's going to remain unless I could find a suitable or better ground for this. If not, then I'll just leave that wire there and not concern myself with it. The standoff is now installed, and the positive terminal now sits exactly over where the old positive terminal used to be. I've desoldered all of the old components from the old positive terminal connector of the old capacitor, and now we're going to resolder everything onto the new terminal over here. At this point, I have 2 of the capacitors in place. This is 280 microfarads, a little bit lower than the original. And like I said before, the reason is I would like to see what the DC looks like before I add the third 80 into this, which will actually bring the filtration higher. But I want to know what the point of diminishing returns was. I want to know if by how much Heathkit decided as a cost-saving measure to stop at 300 microfarads. What was the reason for this? So would adding the 80 make it a little bit better? Would it be significantly better as far as reducing noise on that DC? This is what we're going to find out right now. The oscilloscope will be coming in on pin 1 of the OAY voltage regulator, where we're expecting 145 volts. And that's at 117 volts on the mains, which we'll be seeing more of. So possibly a little higher. But then I'm on the Variax, I could probably get 117. This is also assuming that the OAY can run at its full potential, given the weakness that was seen on that tube. We'll see what we got. I'll also have the multimeter connected as well, so I can look at the reading on the multimeter while I'm looking at the DC and the AC component of the DC. About 70, 80 volts right now, waiting for this to climb. We can see it starting to rise. So we're seeing 125, 126. What are we looking at here? Let's crank it up a bit. Looking at 91 volts. I saw a bump there. So it looks like 142.5. And this is pin 1. This is before the voltage drop through the resistor. It is before the 300 microfarad capacitor. So this is directly off the OA2, 0A2, right? So let's get this moving up. We're at 100 volts. Where are we now? Sitting at 104. Yeah, that regulator's holding solid there. 143 volts. We're sitting at 110. 116. Still 143. 116. And we're going to lock down this variac now at this position. 117 showing 143. In the end, I decided that anybody at Heathkit who would put in a 300 microfarad filter after this voltage regulator, given any money and resources they had, would have put in a 400 microfarad filter if they could. And call me crazy, but I had that extra 80 and it was less than 300, so I threw it in. And this is what we got, and this is as low as I can measure on my voltmeter. That's as low as my voltmeter goes. I'm going to say that this DC, I've gone above and beyond the call of duty to ensure that this DC is regulated and it's clean, and we are ready to do voltages. Let's get started. The diagram never actually tells you what the expected voltage is supposed to be at A. You could see I've already determined it's 125 volts even after this voltage drop. And I'll tell you how. There is one tube that directly connects to A without a resistor, and it is 1/2 of the 12AX7. It's on pin 1. While looking at pin 1 for the 12AX7, we can see it's 125 volts. So I was able to make that determination without it being explicitly stated. I've also gone through and taken measurements of all of these voltages, all the relevant ones. And what I found was there are several instances where the resistors coming off of A to the plate voltages have climbed a bit, or that's what I'm expected to find. And it has thrown off some of these tubes. Further looking at these, I'm going to also find that the resistors that make up part of the bias network for these tubes are going to be slightly off as well, though not terribly off. But I will say, for the purposes of plate voltage, some of them are terribly off. So we definitely can have that. So it's definitely the ones that I marked P, and it doesn't necessarily mean that they're bad. It means that they're plate voltages for those particular tubes, and if they are off, that resistor needs an immediate look, and we're going to find that the resistance has climbed.